kinematics. We're still talking about mechanism kinematics, and some of the basic forms we've already discussed are chains, belts, screw drives, and gears. Let's take a look at the mechanism of a cam. Now, a cam is an object that's used in a lot of machinery in order to transfer rotational motion into linear motion. And to do that, then we have two basic circles, an outer circle and an inner circle, and then the shape of the cam transfers from the inner circle to the outer circle. And as this cam rotates around, there is a follower that follows the motion. And that follower then, as it touches the circumference of the cam, then moves up and down. So as the cam reaches this high spot, then the follower is further away from the center, and then as the cam moves around, then that falls down to the inner circle. So there's your rotational movement, and there's your linear movement. And that's basically how this works. Now, there are all kinds of cams. You can check your textbook to find out what kind of cams there are. But basically, they all act on a principle similar to this. Now, as it goes around, then the follower goes up and down and becomes closer to the center and moves away. Now, at the highest spot, to move up is called rise. So as the cam goes around and the follower goes up, then that's rise. Now, as the follower then goes back down again, this is called fall. So the follower is rising and falling. Now, there's a point at which it neither rises nor falls. In other words, this is kind of a concentric portion of the cam, and so it just rides flat on the cam, neither rising nor falling. And if it neither rises nor falls, it's called dwell. And there are times in which you may have to plan that for what kind of a design you may have. So this is for timing. You find this a lot in automobiles and a lot of other machinery. And so you want to use this application for rotational to linear. Now, to describe this motion of the follower, we can put it into what's called a displacement diagram. And this is a diagram that shows the motion of the cam on a straight line. So we can actually see more graphically what the cam looks like here, instead of trying to decipher what it looks like in its original shape. Now, all we're doing is we're relating the motion of the follower as it moves away from or towards the center of the cam. So this is the rise and fall of the cam. And as it rises and falls, it goes through one revolution. So there's one revolution from here to the end. This is one revolution. And as it goes through one revolution, then, it'll follow the rise and fall. Now, my example here on the board is I've set up the revolutions and divided it into 90, 180, 270, and 360 degrees, which is one revolution. And through that time, I'm going to use 2 seconds. So here at 0.5, 1, and 1.5, and then finally 2. So I can measure the motion of the follower either by the angular measurement or by the time. Now, if I follow this and you take a look at it, you can see this is rise. So through this 90 degrees or half a second, the follower is rising up to a whole inch. Then across the top, it's dwelling. In other words, neither rising nor falling. And then here, as it approaches 180, then it starts to fall. And then as it gets to 180, it dwells again. And then as it gets to 270, it falls again. So it's rising, dwelling, falling, falling. And that will take you through one revolution, and then it repeats itself. It goes around again. So describing then the motion of the follower is easily understood here in this kind of a diagram. So now how do you plan this out kinematically? Well, basically we have to know what the rotational velocity is, and we have, so this is the sum of the time, one revolution over the sum of the time, and we can also then associate that with the change in revolution and the change in time here. So we can determine each individual point along one revolution using this formula here. And then if you want to take and measure the interval of time in terms of a revolution, then, in other words, B being degrees, you find out what the degrees are in relationship to the time, then you use this formula here. So now I can compare these two lines. I can compare the line for degrees with the line for time. And so when I'm developing my diagram here, I can use that formula in order to set up the length of the horizontal line. Okay, so now if you just take a look at these constants here, these variables, they're very similar to what we had seen before. This is the sum of, this is the change in, this is the angle of interval, time, angle of velocity, and the angle in degrees. Okay, so now we can solve problems involving cams, and I have a set of problems for you. So let's get at it and do some problems using cams. Thank you.